Hello everyone. In this video we're going to be looking a little bit at the least upper bound, or the supremum, as well as the greatest lower bound, or the infimum. Specifically, we're going to be investigating the relationship between the two, and maybe the whole point of this video is to kind of answer this last part, which is explain why there's no need to assert that the greatest lower bounds exist as part of the axiom of completeness. When we characterize completeness of R, originally we say what's in this box right here: every non-empty set of real numbers that is bounded above has a least upper bound, but we don't say anything about a greatest lower bound. So in this video we're going to look a little bit at basically why. Okay, so let's recall what a supremum is. So, and by the way, all these little snippets that I have here are parts of the textbook and exercises from Understanding Analysis by Stephen Abbott. So, as usual, the supremum is the least upper bound. So that means that it is an upper bound for the set, but it's also, if there's any arbitrary upper bound, is at least that value of S or greater, right? So the point, as I already said, the axiom of completeness tells us that every non-empty set of reals as bounded above has a least upper bound. And so now we're going to look at the infimum. And so the first exercise is to maybe define it in a similar style. So we can try that, right? So we could say maybe here's our definition. A real number, we might want to, I don't know, call it L. Or maybe, yeah, L. Is the least, no, greatest lower bound for a set A, which is a subset of the reals, if, so clearly we need that L is a lower bound for A, and we need that if L prime is a lower bound for A, then, well, the infimum is the greatest lower bound. So L prime is definitely going to be less than or equal to L. Right? L, we said, was the greatest one, so it is greater than or equal to all lower bounds of A. Okay, there's our definition for our infimum, greatest lower bound or infimum. Let's maybe do this exercise here. Give an example of each of the following, or state that the request is impossible. So a set B with infimum of B greater than or equal to the supremum of B. Well, that seems like backwards, right? The greatest lower bound is bigger than the smallest upper bound, least upper bound. But I would probably say maybe for set A, we could say, maybe singleton 1, which is a subset of R, right? It's non-empty. The upper bound for this is 1. The lower bound for this is 1. This is basically, I guess I should say maybe the supremum of this set is 1, and the infimum of this set is also 1. So they're equal, right? So this is satisfied. Then for the next bit, it says a finite set that contains its infimum but not its supremum. So that means that essentially it has a supremum. It's a finite set, it has a supremum but no maximum. So let's just play with it for a second, right? Let's say maybe I think about a finite set like 1, 2, 3. Well, in this set I have an infimum, which is 1. It's also a minimum. I have a supremum, which is 3. It's also a maximum. So somehow I have to have a maximum, but I have to be finite, but I have to have a supremum but not contain my maximum. Well, the problem is with a finite set, that's not going to be possible, right? Because a finite set will always have a maximum element, and that will be its supremum as well. So not possible. Okay, so the finite set is the important thing there, right? The word finite. Then for C, a bounded subset of Q that contains its supremum but not its infimum. A bounded subset of Q that contains its supremum but not its infimum. Attains its maximum but doesn't attain its infimum. Well, this is not too hard. You can kind of think of like an interval of rational numbers. Not really an interval, but a bounded set. So we could think of maybe the set R is in Q, and maybe we bound R to be between some things. Maybe it's, I don't know, bigger than 1, and it has to contains its supremum. So contains it means that it includes this highest value, and this could be whatever, 5 or something, right? Any kind of arbitrary value. And so there would be an example. Okay. So now we're at the main kind of meat of what we're trying to take a look at here, which is this last exercise, which is to say that if A is non-empty and bounded below, then we can find the infimum using the supremum. I mean, it's just the supremum of this alternate set, which is B. Okay, so for part A, we have A is non-empty and bounded below. B is defined to be basically, just based on the question, the set B is a lower bound for A. The set of all the lower bounds. B is a lower bound for A. So in other words, right, we could say that B is, well, we're not, semicolon, B is a lower bound for A if, right, and we would say that for all A in A is greater than or equal to B. So that's kind of our definition of a lower bound. Some notes. B is non-empty, sorry, capital B. B is non-empty. And we know that because of this fact right here, that A is bounded below, so there is at least one lower bound. Okay, we also know B is a subset of R. Okay, because I guess we assume here A is a subset of R. I guess maybe it goes without saying in this particular example. And we should also mention that B is bounded above. By any A in A, right? Take any A. A is non-empty as well, right? So we know we can do that. Take any A, and we know that it is bigger than any of its lower bounds. So the set of all the lower bounds must be bounded above by A. From all this, we can conclude that the supremum of A, of B, sorry, exists. And from here, the remainder of the proof is to show that the supremum, maybe we'll call K or something, right? So we might say show the infimum of A is equal to K. From here, the proof essentially, I think, breaks nicely into two cases, right? So we can say case 1, B attains, or how about, the supremum of B is an element of B. If that's the case, then the supremum of B is, a lower bound. Supremum of B is the greatest lower bound of A, which is, pretty much by definition, the supremum of B. We'll call it supremum of B equals the infimum of A, right? Pretty much by definition. And then case 2 is that the supremum of B is not an element of B. In this case, we can still prove what we're trying to prove. We just maybe want to do it a little bit more carefully, right? So remember, the infimum has two conditions, which is to say that it needs to be a lower bound, and if we have to take any lower bound for the set, then this is bigger than any of them. So condition 2 is clearly satisfied, right? So suppose L prime is any lower bound for A, then we have that L prime is less than equal to this K, right? This supremum of B. I don't know, I'm kind of not really using K, so maybe we'll just say supremum of B. Okay, so that's satisfied. But the condition was that we needed the supremum of B, should, so that's the other condition, right? Should be a lower bound for A. So we're going to proceed by contradiction here to show that this case essentially doesn't happen, right? To say that this is not a lower bound. We're saying here this is not a sub B is not a lower bound for A. And we're going to essentially proceed by contradiction. So, supposing this, that means that sup B is not a lower bound for A. This means that there exists some A in A such that A is less than the supremum of B. But if we have that A is strictly less than the supremum of B, we have that A is not an upper bound for B. But that means, right, that there is, so A is not an upper bound for B. That means that there is some B in B such that B is strictly greater than A. But this is a contradiction because B is in B, which means it is a lower bound for A, but it's bigger than an element of A. So it can't be a lower bound. It's strictly bigger. Therefore, contradiction. And so this case doesn't happen. So we just have this case right here, and the proof follows. So we don't need to assert that there exist greatest lower bounds because it automatically does, right? So we don't need to include, and every non-empty set of real numbers that is bounded below has a greatest lower bound. That part follows from this by just thinking about the argument we did here, which is this set of lower bounds for A. Okay, that's all for this video. Thanks so much for watching.